All right, hello and welcome. So, you're gearing up for your STPM exams, and that means we've got to tackle the big topics head-on. Today, we're diving into one of the most important ones, the application of differentiation. Seriously, this is like a superpower in your calculus toolkit, so let's get right into it.
Just think about it for a second. In the real world, and definitely in your exam questions, we're always trying to find the best of something, right? What's the highest altitude a project can reach? What's the absolute lowest cost to manufacture something? The fastest way to get from A to B, or the cheapest design that still works? How do we actually figure that stuff out with math?
Well, that's exactly where differentiation comes into play. It's so much more than just finding the slope of a line on a graph. It's the engine that lets us pinpoint those maximums and minimums to find the absolute best, most optimized outcome in pretty much any situation you can think of.
Okay, so let's dive in. To find the highest peak or the lowest valley on a curve, our first job, our first mission, is to find all the spots where the curve goes completely flat for just a split second. In calculus, we have a special name for these spots. We call them stationary points.
So what is a stationary point, really? The name itself gives you a huge hint. Imagine you're hiking up a hill. At the very top, right at the peak, the ground is perfectly level for a moment before it starts going down again. Same thing at the bottom of a valley. That flat spot? That's a stationary point. And mathematically, it's the precise location where the gradient is exactly zero.
So how do we hunt them down? It's actually a super simple two-step process. Step 1, you find the derivative of your function, f prime of x. Remember, that's just the formula for the gradient. And step 2, you take that derivative, set it equal to 0, and you solve for x. That's it. The answers you get are the x-coordinates for every single flat spot on that curve.
But, finding a flat spot is only half the battle. Once we find one, we have to ask the next big question. Is it a peak, what we call a local maximum? Or is it a valley, a local minimum? We need to figure out what kind of point we're dealing with.
And for this, we've got two main tricks up our sleeve. You can think of the first derivative test kind of like a detective. You check the gradient just before the point and just after it. If the slope goes from positive to 0 to negative, you've found a peak. If it goes from negative to 0 to positive, you're in a valley. The second derivative test is a bit more direct. It's like using a microscope to check the curve shape right at that point. Is it curving upwards like a bowl, or is it curving downwards like a cap? Both tests get you to the same answer. Now this is where things get really cool. Once you know how to find these special points and figure out what they are, you're not just looking at random dots on a graph anymore. You now have the power to understand the entire shape of a function and sketch it out. So here's your go-to checklist, your game plan for sketching any curve. First, find those stationary points, where f prime of x equals 0. Second, figure out if they're maximums or minimums. Third, you look at the spaces between those points to see where the function is going up or down. And finally, you put all those clues together and you can draw the whole thing.
So how do we know where the function's rising? It's super easy. In any section where the derivative, f prime of x is positive, greater than 0, that means the gradient is positive, the curve is going up. Simple as that. You're climbing the hill.
And on the flip side, if that derivative is negative or less than 0, then the gradient is negative. The function is going down. It's on a downward slope. These two simple rules are all you need to fill in the gaps between your stationary points.
All right, now we get to the main event. This is where all these skills, finding points, classifying them, understanding the curve, all come together to solve those real-world problems we talked about at the beginning. This is optimization.
And you're going to want to pay close attention here because this is a huge focus for your STPM exams. You will see problems that ask you to use differentiation to find the best answer. Stuff like, what are the dimensions of a box that will give you the maximum volume? Or what's the production level that gives you the minimum cost? This is it.
So here it is, the 5-step game plan for crushing any optimization problem. First, figure out your variables and any limits or constraints. Second, build the main equation for whatever it is you're trying to maximize or minimize. And from there, hey, it's the stuff we just learned. You differentiate the equation, you set it to 0 to find the stationary point, and then step 5, you just double-check that you've actually found the max or min you were looking for.
So as we start to wrap this up, I want you to remember something really important. What we're learning here, it's not just for this one chapter or one exam. This is a foundational bedrock concept in all of mathematics.
And this is so key. Mastering differentiation is what opens the door to all the other big topics. You literally cannot understand its reverse, integration. without it. And it's the absolute heart of differential equations, which are used to model everything from how populations grow to how electricity flows. It really is the cornerstone.
So I'm going to leave you with this thought. You now have this incredible mathematical toolkit that lets you find the best possible solution to countless problems. You have the method. The only question is, what problems are you going to solve with it?